I guess I'd like to start by thanking everybody for taking time to join and let you know briefly what we're going to be covering this morning is really a basic introduction to SIS. We're not going to deep dive today into some of the more complex parts of SIS, but the goal is to give everybody a general understanding of SIS so you can have hopefully a good, intelligent conversation with customers, understand some of the terminology, understand the customer's needs when it comes to SIS, and know a little bit about the background of SIS and how it's impacting our world today and in the future as well. So that's really what we're going to try to do here in the next hour. I'll get started. Derek, unless you had anything else you wanted to say, I can get going.
No, please, jump right in. Thank you.
Okay, well, terrific. So let's just, looks like I have to close that. There we go. Okay, so just a little bit about myself. I've been in the valves and controls industry for over 20 years and been specializing in custom automated packages for about the last 18 years, specifically focused on oil and gas and petrochemical in the Pacific Northwest and then including Alaska. As SIS became a big part of our lives in the oil and gas industry, I ended up sort of delving into SIS just because it was something our customers were quite focused on. And then over the last several years, been involved in contributing to or writing a lot of articles on SIS for hydrocarbon processing and valve world, et cetera. So fortunate to have traveled around the world in the last couple of years, meeting with SIS experts all around the world. So some of the message I bring to you today will be kind of a worldview, which is, I think, advantageous for us as well. And then just jumping in right off the bat to the standards themselves, basically about 20 years ago, the world kind of looked around at what we were doing to be safe around hazardous process piping and determined that what we were doing really wasn't working well enough. With the introduction of the microprocessor, a lot of things began to change in our industrial plants. A lot of automation began to come in. There wasn't a lot of standards around that type of automation. At the time, what was really kind of the most common safety focus was best practices. And everybody was doing something a little bit different when it came to best practices. So the determination at that time was some new standards needed to be developed to address this. One of the incidents that really kicked this off was probably the most horrific industrial accident in our lifetimes in Bhopal, India. It killed hundreds and hundreds of people. It was devastating, and it was kind of a wake-up call to the whole world. So experts from around the world got together, and in combination with the ISA and also the IEC, International Electrotechnical Commission, they began to develop some new standards. And the two standards that we're going to focus on today are IEC's 61508 and 61511. And if anybody on the call has been involved in projects that involve spill, which I imagine many of you have, you've probably seen these standards, these references on projects and RFQs and on specifications. And it's very helpful to understand kind of where these two different standards come together and also how they're different. So if you look there in blue, right here, IEC 61508. This is a standard that applies mainly to OEMs and manufacturers and suppliers of the devices and components in an SIS, and we're going to talk in a little bit about what all those components are. But this is the standards around which they do deep dive analysis on the components to determine the reliability of the components themselves, ensure that those components meet a certain level, SIL level specifically, of reliability, and then certify those components for the 61511 standard, which is really the design and the development of the whole system. IEC 61511 applies mainly to the designers, integrators, and end users. Specifically, end users are responsible for 61511 implementation in their plants. And so this is really where the two kind of handshake together is you are required to utilize 61508 compliant devices in your 61511 designed system. So this is how the two operate together. So the design purposes for these was really to develop standards to protect personnel, equipment, and the environment, and mitigate the likelihood of potential risk in our plants today. They really want this system to bring a plant to a safe state if there's any sort of upset condition. So they set these limits, whether it's temperature or pressure or flow, and when any of those kinds of things are exceeded and a dangerous, potentially dangerous, hazardous situation is likely, then this system kicks in and it brings the plant to a safe state. It's commonly emergency shutdown or interlock safety shutdown systems, and that's really the essential part of the SIS, is to bring the plant to a safe state. One of the confusing points out there is a lot of people ask, well, the standards, I thought the standards told our customers exactly what they have to do, but Shell does one thing, Chevron does something else, Dow does something else. They all seem to be doing something a little bit different, and that can be confusing. And the reason for that is these standards don't define exactly what the customers have to do, but instead the standards lay out a framework that each individual customer can, or designer can, design their system around, and they can sort of develop their strategy within the framework. So that's why you might see one customer for this piece of equipment, say a heat exchanger, they're calling the valves around their heat exchanger for SIL 1, and meanwhile the very next customer is doing the same application and they want SIL 2. And we'll get into those SIL levels and how those are applied. And we're going to talk a little bit about this framework itself and how it applies to customers and different strategies that they might utilize, and why we might be seeing different SIL levels for the same application. So first we'll get into understanding some of the terminology and some of the processes around 61511. Many of you have probably been trying to set up meetings with customers, and they can't meet. They're busy, tied up in HAZOP or PHA meetings. PHA is Process Hazard Analysis, and HAZOP is Hazard Operability Study. And basically what they're doing at the customer level is they're putting in a room a group of different disciplines from their plant to take a look at where are the most hazardous places in their plant. They're doing a study to determine what pieces of equipment, fired heaters, heat exchangers, vessels, high-pressure pumps, etc. And as they begin to look at what hazards exist in their plant, they drill down as if through layers of an onion. And you can kind of see here in the top right, this diagram gives you an idea of what they're doing in these HAZOP and PHA meetings. So they begin to drill down, first of all, looking at outside the plant, what's the community emergency response for safety? Within the plant, what's the plant emergency response? What are they doing to mitigate hazardous situations within their plant with mechanical mitigation systems and safety instrumented control systems? And then finally, all the way down to basic process control systems. And they just keep drilling down, analyzing what are the hazards and what are they doing to be safe. Within this process, they have a couple different methods for doing statistical analysis of what layers of protection they have. One of this is called LOPA. You see in the middle of this slide, layer of protection analysis, and that's really a deep dive analysis, both quantitative and qualitative analysis of what safety systems they have in place. Layers of protection is very important. For example, if they take a look at heat exchanger and they have not got enough layers of protection around that heat exchanger, this is where they identify that they need to develop a more robust safety system, and it's also where they may be generating business for us, for example, because through this process that they determine they may need additional shutdown systems. That might include sensors, logic solver, and automated valve packages or final elements. And a little simpler way to explain this is in the bottom right-hand corner, you see this is called the calibrated risk matrix. And they're doing something similar to LOPA, but much less heavy lifting on the analytical side. And as you can see on this calibrated risk matrix, it shows on the vertical arrow the likelihood of an event. So we're looking to determine for every piece of equipment in the plant that is hazardous, what is the likelihood of an event? And then the horizontal line is the severity, or a better way to describe that would be exposure to loss of life or exposure to people. So what is the likelihood that an event could occur with this piece of equipment? And then if something does occur, what would the potential severity be or exposure to loss of life? And you can see here they're assigning SIL level based on low to moderate or high likelihood or exposure of severity. And so this is how they're kind of quickly determining SIL level. So this group of people in the HAZOP may be sitting looking at a heat exchanger, for example, that's at the very back of the plant. There's not a lot of personnel at the back of the plant. They may determine that this has a very low level of likelihood and also a low level of severity, and so we may classify that as a SIL 1 application. However, we may have a heat exchanger right outside our operations building where we have at any given time 30 personnel, for example. Well, that would raise the severity significantly, so we may be bumped up to SIL 2 on severity just because we've got more exposure to loss of life. And so that's a very simplified explanation. Of course, LOPA is a much deeper analysis to arrive at a similar place, though. They basically need to assign SIL level. And this is a little bigger blow-up of that calibrated risk matrix. Some of our customers use the calibrated risk matrix in conjunction with LOPA instead of as an alternative, in which case they may determine that everything SIL 2 and above that they assign a LOPA to. Now, the reason they might do that is LOPA is very expensive. It's a lot of engineering. It's greater cost to the customer. So they may use these in conjunction with each other. So let's take a look at a few more terms. Safety Instrumented Function, or SIF, is something you may hear frequently talking with your SIS engineer. The SIF is when you've drilled down and down and down through those layers of the onion that we looked at earlier, and you arrive at around a piece of equipment. On the top right, you'll see in this diagram you've got pressure sensors, temperature sensors, flow sensors. So your SIF is made up of sensors, logic solver, and a final element. And the final element is the automated valve package. So you may have many, many SIFs around even one piece of equipment. So each of these SIFs constitutes a small subsystem of the SIS. Now, SIL stands for Safety Integrity Level. And the SIL levels go from 0, which would be the lowest risk, all the way up to 4, which would be the highest. 4 we call the unicorn in a sense because we don't see SIL 4. I've not ever seen SIL 4. However, SIL 3 is somewhat common. We see them in HIP systems. We see them in some refinery systems. SIL 3 is the highest that we're seeing in industry today. And each one of these, SIL 1, 2, 3, goes up in order of magnitude more reliable than the previous level. So each level that we go up is becoming an order of magnitude more reliable. Some other terms, spurious trips. This is a term that comes straight out of IEC 61511. This is the bane, really, of existence for safety shutdown systems. Spurious trip is basically a trip of the system that had nothing to do with a hazardous event, but had something to do with some sort of failure or fault within the system. These are unfortunately very common, something our customers battle on a regular basis, something they want to do everything possible to eliminate, and it's a great opportunity for us to get involved and offer our assistance. And so we're going to come back to spurious trips a little later in the presentation and focus on that. Another term that you'll hear is probability of failure on demand, or average probability of failure on demand. The PFD average is specifically the analysis of the reliability of the components going into the system. So when we do our 61508 component analysis for SIS, we develop an average probability of failure on demand. So a little more clearly way to explain this would be when we look at a device based on proven in use data, how long have these been installed, how many of these have failed, how did these fail, what components failed, what engineering processes are in place to manufacture these devices. So this big deep dive analysis is done, and a PFD average is developed, and that is how long can we expect this component to function reliably before it fails. And every component that goes into a safety instrumented system has to be certified to 61508, and you'll find this average probability of failure on demand in the certificates for all of these components. What a SIS engineer does is they sit down and they take the certificate for each of the components, the sensors, the logic solvers, the final elements, which includes the valve, the actuator, the controls. And all of these, they take the PFD average from each one of these certificates and they put them into a deep dive analysis software, typically softwares like SIL Solver or Excellentia. Shell has their own proprietary software system. But basically, they plug in these PFD numbers into their calculations along with other system design criteria, which we're going to discuss. And out of these calculations comes the final risk reduction factor. So when you start to combine all these, obviously, if you have a product that has a better average PSB number than another product, that will directly impact your risk reduction factor. So there's some other things that impact the risk reduction factor that are part of the design criteria, like hardware fault tolerance. You see at the bottom of the page here. And really, hardware fault tolerance could also be translated as redundancy. So, for example, if we're trying to make a system more robust, if we have one pressure sensor and everything relies on that one pressure sensor, that impacts our risk reduction factor. We're relying on one device. However, if we add another pressure sensor and we add voting, so 1 out of 1 or 1 out of 2 voting, we now have 2 devices. Our system is more robust. We need both of those devices to be reporting an over pressurization to our system before we trip our safety system. So we've got a more robust system, and that increases our risk reduction factor. So you might see dual solenoids on automated valve packages. That's another way to address hardware fault tolerance. You might see more than one valve, for example, on SIL 3 systems. You're going to see typically 2 valve packages, 2 final elements. By putting in that redundancy and building up the robustness of the design, they improve their risk reduction factor. When our customers are designing safety instrumented systems, they typically assign a targeted risk reduction factor. So this is a target that they would like to achieve with their SIF, safety instrument and function, which is the sensors, logic solver, and final element. And so we can help them impact some of these areas of design by helping them develop more robust automated packages that have less likelihood for spurious trips. Spurious trips can be caused by a lot of different factors, and we're going to discuss that a little bit more coming up. We also can help them validate the PFD average numbers for all of the components, make sure all of the components we're supplying will meet and comply with the SIL level that the customers have specified. And really just getting a general discussion with our customers about the specifications around the final element and help them with a strategy to optimize these packages. So once again, just a little review, taking a look at what is a safety instrumented system. These are the components that are part of the SIF, the sensors, the logic solver, and the final elements. Now, the safety life cycle is another term that you'll hear frequently in discussions with your SIS engineer, and this is simply all of the processes from the very beginning of conceptual design, engineering, specifications, all of the realization phase, validating, planning, through commissioning and startup, and all the way through to eventually decommissioning. Another way they term this is cradle to grave. So the safety life cycle really starts right at the beginning of engineering design, goes all the way through to the decommissioning of the equipment. We as manufacturers and representatives of the manufacturers, we really can play a huge role in each one of these 3 phases, the analysis, the realization phase, and the operational phase. It's a real advantage to us to get involved early. We know as an overall sales strategy that the earlier we can get involved in projects, the more opportunity we have to influence specifications, to build relationships with the key decision makers to, to really reap the greatest reward, I guess, from a project. If you're just getting involved in a project at the RFQ level, you've really missed all of your greatest opportunities to influence the project. The great thing about SIS is they do need us involved early because we have the knowledge and the expertise and the engineering background as the OEMs and as the representatives to help them strategize up front in their front-end engineering and design and help them through all of this life cycle process here. And then all of that process, all of the analysis, all of the data, all of the specifications, it all gets rolled into the safety requirement specifications. Every plant has their SRS. They're required to have their SRS usually through their safety. But one of the questions I get frequently is, are these standards mandatory? And they are not mandatory. And that's surprising when really all of our customers are trying to comply. So then the question is kind of, why are they all working so hard, spending so much money and resources to comply? There's a few different reasons. Really, they would say, first of all, they want to be safer, and these standards are designed specifically to help them be safer. But also a little bit of reality is they want to reduce their exposure to liability and potential lawsuits, whether that's due to environmental damage or damage to personnel or even damage to their own equipment. So really everybody is self-complying at this time, although we have seen some hints from different supervising authorities like the United States Chemical Process Board. They have done some investigations and released some reports where they've hinted at mandatory compliance. I think that's probably the direction that we're going, is someday we'll see these change from being standards to codes, at least in some form. Similar to, if anybody on the call does work with pressure relief valves, you know that there are specific codes that customers have to follow with pressure relief valves. There's testing requirements. There's fines if they don't follow those codes. Those are enforceable codes. We really see these standards eventually, at least parts of them, arriving to a place like that where they become more like codes. So some subsystems of SIS that we're going to focus on in the rest of the training is emergency shutdown systems, which probably constitutes somewhere in the 70% plus of applications that we see with our customers, and also high integrity pressure protection systems. We don't see this as frequently. We see it in a lot of offshore applications, some onshore applications. We'll talk a little bit about that, but I'm not going to spend a tremendous amount of time on HIPS. Just give you a brief overview. So high integrity pressure protection system, typically this is what a HIPS system looks like. Once again, you've got your sensors, logic solver, and currently you've always got two shutdown valves or final element packages. They're typically double block and bleed ball valves for the most part, although there's some great opportunity for triple offset valves in this application. That really is an area where we need to continue to educate our customers on triple offset valves and how they function and what their benefits are, so that we can see more triple offset valves installed in these applications. But really there's no reason they can't be unless the line needs to be pigged. And if it needs to be pigged, of course, now we're talking about full port ball valves. Why would somebody install a high pressure protection system? So let's take a look at a few of the most common reasons. typically, when you've got a high-pressure system, you've already got pressure relief valves in place to protect vessels and piping, etc. However, if the flow rates through those relief valves was excessive or could be excessive in certain conditions, they may want to install a high-integrity pressure protection system in addition to the relief valve. If toxic gases could be released, they may want a HIP system. If there could be significant environmental impact or potentially, fines, for example, if they have a flaring capacity that could be exceeded with a discharge, then there's big issues with that. So they may need a HIP system. If they want to minimize the loss of their product, they don't want to flare off a lot of that product and lose it, they may install a HIP system. So these are some of the most common reasons that customers install HIPs. We do see them, all the time in offshore because of the high pressure processes that they have in offshore. And as I said, ball valves are the most common valve solution, although triple offset valves are acceptable in most applications. This is a typical HIPS loop. We already took a look at one example of this where you've got your pressure transmitters, your logic solver, and then your final element composed of failed closed valves. This is the offshore application I was mentioning. Typically, these are the subsea flow lines, highly pressurized. We see HIPS, nearly every offshore application we're seeing HIPS. And then we move into emergency shutdown valve. And this is really the most common application that we'll see for our SIS systems. One of the, can be confusing issues with emergency shutdown valves is there's many different acronyms that our customers use to refer to the exact same device. They can call them ABVs, automated block valves, EBVs, emergency block valves, shutdown valves, emergency shutdown valves, emergency isolation valves. So, there's a lot of different acronyms for these, but really they're referring to the same thing, and that is these are all automated emergency shutdown valves. Now, they can be fail open, fail closed. Typically, none of these are ever fail last for SIS. So we're looking at failing these to a position specifically. Now, one of the questions I get all the time is why, as a valve and actuator OEM, are we presenting on SIS, or why are we so focused on SIS as the OEM of these components? And this slide ties this whole presentation together. When I was telling you earlier about the calculations that are done through softwares like SILSolver and Excellentia, where we take all of these PFD averages and we start to combine those together with the system design criteria and hardware fault tolerance, all of those calculations to arrive at the risk reduction factor, this is how those calculations are weighted. If you see that pie in the middle, 42% of the weight of those calculations falls on the sensors, and 8% falls on the logic solver. And this is very conservative, by the way, this analysis. And 50% of the calculations falls on that automated valve package on the final element. Really, this is conservative. It's usually much more than 50% of the weight on the automated valve package. So taking a look at that as an SIS engineer with one of our customers' plants, it's clear to see that the people who can impact safety and optimize the system and that are potentially a biggest part of our SIS system is the automated valve package. And there's a few different reasons for this. Really, sensors are, electronic pieces of equipment, logic solvers as well, very highly known probability of failure on demand when it comes to those. when we look at the final control element, we're now talking about a lot of different variables that can be put into play. Probably most importantly would be the fact that this is a device that's mechanical and it's in line with the media. So if we think of this in terms of, applications out there like sulfur vapor recovery, where it's very sticky and we can get all kinds of valve failure caused just by the application of the process as well as the application of the valve. So we've got a lot more reliability issues and concerns with the final control element. So this is really what brings us to the table in SIS and why it's such a big focus for us. Now, you would think with these high fill rated packages, automated valve packages, that and all the engineering and design and analysis and all the resources that goes into developing these safety shutdown systems, you would think that we would not see a very high failure rate. However, that has not been the case. There's been, unfortunately, a high failure rate with safety shutdown systems. Many of our customers have been doing research and working with end users and focus groups, process industry experts like WIB and ARETA and ISA and EUV and Exida, to name a few, that have been doing deep dive analysis on these failures, trying to determine why are we still seeing a fairly high failure rate with emergency shutdown valves, and especially spurious trips. That is a big concern with emergency shutdown valves. And what they found is at the bottom of this slide, you'll see those 4 points. These are the 4 areas that they found were major areas of concern or areas that had caused failure in the field. And the first one you see is valve torque coefficients and application life cycle analysis. So what they determined here was that there had not been adequate application life cycle analysis done in the applying of the valve to the process. And so like the example I brought up earlier, sulfur vapor recovery, somebody's specifying a valve into clean hydrogen, and they're putting the same valve into sulfur vapor recovery and experiencing failures. And so they defined this as a area of concern and an area that they need to develop some new, really new approaches to address this, to make sure that proper life cycle analysis is done on the valve as it's applied to the process. Second of all, they determined that they had a lot of bracket and coupling and really drivetrain component failures of one kind or another. This could be due to a lot of issues, under-engineered bracketry. When we're talking about some of these ESDV applications, we've got large, high-pressure metal-seated ball valves with very robust shafts and a massive actuator to actuate that valve. And now you've got to make sure that the bracketry and drivetrain components are designed sufficiently to handle the loads and the stresses. And they found this was an area of failure that had not been addressed correctly. Actuator torque coefficients and safety factors was a huge issue. Actuators being undersized, actuators being oversized, all kinds of issues with specifying the actuation. And some of these tie together. For example, if the valve torque coefficients were not, the analysis was not done correctly, for clean hydrogen, your valve is not going to see typically a large increase in torque over its life, but in sulfur vapor recovery, of course, we can anticipate that there's going to be an increased torque requirement from the valve over the life cycle of the valve in that application. And so that needs to be taken into account when the actuator torques are selected and designed. And finally, in the actuation, integration, assembly, and testing, they found issues, whether it was undersized tubing, solenoid valves not sized sufficiently, all kinds of different systematic issues that develop around the integration and assembly of the package. So these were four major areas when it comes to the final element that were identified as major red flags and areas of concern. Well, the reason this is of importance to us is these are areas that we can specifically address and help our customers develop a strategy around these. We bring the expertise, the engineering, and the knowledge really around these 4 points to our customers. This is really where they need us to get involved and help design and optimize the systems. Within that design and within that engineering, there's a lot of things that they need to support them. On the top left here, this is an application lifecycle analysis that we do for the Vanessa triple offset. This is a sizing program that we have that takes a look at the process conditions, determines, do we have too much noise across this valve? What are the torques truly going to be for this valve in this application? This is very critical for all valve applications in SIS. We're talking about safety. We're talking about people's lives, and I think it's important to get involved with our customers at this level, doing a deeper dive application analysis, whether it's ball valves or triple offset valves or butterfly valves. When it comes to the actuation torque analysis, we really need to develop the right strategy. We're the people that manufacture and represent these components, and we know how they should be applied. We know whether, for example, to be using a symmetrical yoke or a canted yoke. We know how those torques apply to the valve. So these are critical things. Fill verification for the automated valve package is extremely important. We are building up a program within Pentair where we have people that can do this fill verification module in the bottom left-hand corner. Really, what we're doing here is we're taking all of the PFD numbers from all the certificates for each of the components in the automated valve package, and we're making sure that the combination of all of these components provides the proper fill level so that we know that we're compliant for our customer. And then again, customers need drawings and schematics are critical for these types of packages. So really, this is some of the most highly engineered and complex automated valve packages that we're seeing in our industry. But some of the testing criteria for these SIS packages is pretty extraordinary. This is an example of a package that we built for a customer in Germany. These valves, I think they were 12-inch Vanessa valves. They needed to close in 300 milliseconds. This is not only a challenging task, but I would say testing and proving it out is even more challenging. But this is the kind of work that we're doing at Pentair and the kinds of things our customers are asking from us when it comes to SIS. So we do see much more complex testing requirements when it comes to these safety shutdown systems. The good news is, we as the manufacturer at Pentair, we've been involved from the very beginning in SIS. This is BIPI's certificate. As you can see, they were involved with IEC 61508 all the way back to early 2000s. And this is a great message. There's a lot of value message that we bring in this to our customers. First of all, the legacy brands. We've been building and installing our components into SIS systems around the world from the beginning. Because we've been involved from the beginning, we have some of the best engineering experts and expertise in the world when it comes to SIS and applying our products and our components into their system. So this is a big advantage for the customer to understand. Excuse me, we did not just get involved in this recently, but we've been involved from the beginning, and we bring all that knowledge to bear for them. As the manufacturer, we feel that the sum of all of the parts is greater than the individual components. So really, what I mean by that is, developing a automated valve package that is engineered, designed, and optimized to work correctly, to work reliably for our customers, to meet the needs for their application, to satisfy their SIL requirements. We're uniquely qualified to help them in that. And they really are leaning on us more and more to help them develop strategies for their final control elements, especially in cases where we're providing all of these components from one OEM. It's our valve, it's our actuator, it's our controls. Then we play a huge role in what we can do for the customer. So just have about 10 minutes left. I want to make sure I cover this. Spurious trips. I told you this is a big concern for customers, and I'm going to get into a little bit more of the reasons why. And this is something that hopefully after this training you feel comfortable bringing this up with customers. Feel free to ask them. Are you guys seeing a lot of spurious trips with your safety shutdown systems? Well, why would that be an issue? Well, these are unplanned shutdowns. These are shutdowns that come from false or systematic failures. A lot of times they have to do with the final control element. There's several different issues around that automation package that can cause spurious trips. There's a significant cost to the customers, not just in safety risk, but financially when it comes to spurious trips. This is a little better way to explain it. So what happens when the system, out of the blue, trips off? Well, a lot of times it shuts down the process, which is really a big issue for the customer. But even more importantly, it can be a cascade trip. So it wasn't just one valve, it was several valves that trip closed. So the first people who need to get involved here is operations. They've got to get out and try and determine, what tripped the valve, see if it's something simple they can address. If it's not, they have to get maintenance involved. If it's over their heads and it's something deeper and more complex, they have to get engineering involved. And so it puts a lot of demand on end-user resources to get involved immediately and get back online. And there's a big reason for that. You see the clock at the top of the red box. The clock is ticking from the moment this spurious trip takes place. And if the process is down, a significant amount of dollars is being lost while the process is down. I've seen complete units taken down by spurious trips. So it can be big bucks ticking away. The problem is they want to get back online as fast as possible, but they've got the pressure pushing down from management at the top to get back online, and the pressure pushing up from the bottom is safety, because despite all of the financial pressures, they've got to have concern for safety. And so in this decision process is where the end user is living, and it's this very high-pressure environment, really largely caused by the final control elements, the automated valve packages. And so when we look at this, I think talking with customers about this and them seeing that we understand that this is the world they live in, that this is one of the big issues they deal with when it comes to our products that we're providing. And this is the area where we can really help them develop strategies. For example, we can help them with developing a strategy with great control components that provide more diagnostics. Number one, it gives them more diagnostic coverage, which impacts the risk reduction factor. But number two, it's the most critical part of what they're going to do when it comes to spurious trips. They need to be able to diagnose what was the root cause of the spurious trip. And in addition to more data or more diagnostic data, they need it to be credible data. So empowering this team of decision makers at the end user level, this is an area where we can get in and make a big difference. Now, of course, the end user is excited to hear what we have to say about this, but so also are the EPCs, the engineering and design firms as well, because they want to design a system that their end user is proud to own, that works well for them, that's reliable, that provides powerful diagnostics. So this is really an area that we can discuss with everybody throughout that safety life cycle that we talked about earlier. So specifically, how could we address that? You know, we have the Westlock Digital Epic 2 as a control device that is a great topic of discussion with our customers, discussing how we can add diagnostics and more credible diagnostics through this control component, how this control component can impact their partial stroke testing strategies and stroke testing. So one of the portions of the standard tells customers a framework for stroke testing. So they know they have to stroke test, and it can become difficult to write procedures around stroke testing in some of the environments with our customers. For example, sulfur vapor recovery is not easy to shut that process down and bring that process back up. So one of the ways they can extend the proof test interval is by utilizing partial stroke testing. Unfortunately, a lot of the devices that have been out there for partial stroke testing, like positioners have a lot of inherent issues when it comes to partial stroke testing. They're very, very complex designs for systems with positioners so that they can do partial stroke testing. For example, the positioner does not utilize the solenoid valve for the partial stroke test. So some customers have thrown this completely out and said we won't do partial stroke testing unless we add in another position transmitter and some other components and design a very complex system that does more than just pulse the solenoid valve. So we get pretty deep here, and this is part of the Westlock Epic presentation. And if you have responsibility for this product, I would encourage you to get some additional training specifically on this product, because it's a great area that we can go in and talk with our customers about reducing spurious trips, adding more diagnostics coverage. You can see here, this is some of the pros of using a position transmitter. We actually use the solenoid valve for the test. That's a big, big advantage. While we're in partial stroke test, if there's an emergency, this emergency shutdown valve is still available. It is not available typically in the positioner scheme. So several advantages to using this device. And just one of the ways that we can help our customers optimize the system. Some of the diagnostics capabilities of that control device allows us to have some predictive maintenance rather than reactive maintenance. So we can predict that we're starting to develop some valve issues, potentially packing, torque increasing, print airline. This is very common. We start to see not enough air volume to stroke the valve correctly, seat failure, all kinds of issues can be diagnosed with the Digital Epic 2. And again, as I said, I'm not doing a training on this today, but this is something I would recommend that you put more effort into learning about if this is a product you're responsible for. So these are some of the major areas of concern that our customers have when it comes to SIS that we can get in and help them with. So In the top right-hand corner, safety, of course, they want safer solutions. They want to improve their risk reduction. They want to have a high level of equipment availability. They don't want this equipment going down, dealing with spurious trips. They want to make sure they comply with the safety standards. So a lot of areas where we can get in and help our customers when it comes to safety. We can help them reduce their lost production time. This is huge, major dollar savings here. Maybe the most of all of the areas that we can help them save money when it comes to lost production by reducing spurious trips, reducing their downtime, helping them get back online safely and quickly, extending their proof test intervals so they don't have to shut down their process to do full stroke testing as often. So there's a lot of different strategies we can help them with specifically in that area. Then OpEx, of course, the things that I was just discussing, being able to get in and diagnose something quickly and get back online, that's a very powerful way to impact OpEx costs. I mean, every time all this crew needs to get involved in solving spurious trips, it's of great cost to them. It enables them to do predictive versus reactive maintenance. It enables them to go automated on their partial stroke testing versus using human dependency for that. So a lot of big advantages there. Then we move to CapEx. This is important on the front-end engineering and design, where we can involve ourselves and impact the cost on projects for EPCs and for end users by helping them optimize the automated valve package, making sure that they, for example, have not oversized significantly an actuation package. You extrapolate that over 10, 20, 30 valves on a project, and that can become quite costly, and that's where our engineering expertise comes into play. We can help them be sure that they are complying with the process safety standards. We can make sure that they're giving them a sole source of accountability for the whole package. So there's a lot of different advantages and benefits to working with them on the SIS. Of course, Pentair manufactures ball valves, triple offset valves, butterfly valves. Really, we have a lot to offer when it comes to SIS. Automation and controls, whether it's hydraulic, electro-hydraulic, pneumatic. We really have a wide range of automation products that we can offer our customers. All of these utilized in SIS. Controls with our Westlock line, we've got Digital Epic 2, but we've also got fill-rated switches. Depending on the application that the customer has, we can help them with controls. It's getting close to time ending here, so let's just talk about this for a few minutes, and then I'll open up for questions. So just a quick look at why SIS as a strategy for us in the sales group. It's a large opportunity worldwide. SIS is impacting the EPCs, it's impacting the end users, oil and gas industry, downstream, midstream, upstream, petrochemical, chemical, pulp and paper, power, mining. If it's hazardous process piping, SIS is becoming involved with that. So it is something that we need to start putting our focus on with our customer. Modernization in SIS is really a hot topic. I think we have close to 30 people on this call, and I think that represents in and of itself how hot this is right now for us, much more so even for our customers. A lot of large capital projects and MRO projects are ongoing to modernize and automate their facilities for SIS. So it's great. We mentioned it to customers, and I think, Jim, as you said at the outset of the call here, you guys are looking to put something together for your customers. All around the world where we've offered some of these SIS presentations, the response is overwhelming. It attracts a unique audience, and this is one of the most amazing things I think that we've seen with this is if you were going to a customer or to an EPC to present any single one of these products, you would get, a relatively small response in comparison to SIS. If it's, for example, ball valves, we're going to do a lunch and learn on ball valves. We only reach so many people with that presentation. The SIS presentation tends to draw people from multiple disciplines, whether it's EPCs or end users. We've got purchasing, we've got project engineering, we've got reliability, we've got safety, controls engineers, mechanical engineers, maintenance. I mean, it's a really diverse group, and a lot of our most influential decision makers are in the room, so we can develop a great amount of credibility with all the right people. It enables us to differentiate ourselves, our product, and our solutions with the customer, and we're always striving to do that. So that's a great opportunity. It gets us in early. So leading with the SIS technology enables us to get involved in the feed process and really be involved throughout that whole life cycle that we talked about earlier. It's also helping us, raise our margins back up. Unfortunately, over the last 10 years, we've seen a big erosion in our margins in our industry as a lot of our automation has become more commodity. As example, the HVAC industry, where we used to sell automated valve packages and they were considered an engineered solution, that industry has very much become a commodity. And unfortunately, once products develop into a commodity product, then we're talking about things like pricing, and delivery, and it's really tough to differentiate, on technical advantage. So we bring that back into play here. Again, I said already, we differentiate our sales force, we raise our technical skill and ability of our salespeople, and we develop credibility around something that's very high visibility for our customers, that's safety related. So big advantage for us. The market itself is estimated to be really over $3 billion over the next 5 years in just this automated, engineered package world. So it's a huge opportunity going forward. And really that's all I have. I tried to cover a lot in a short amount of time, and if anybody has questions, I can go ahead and field those for a few minutes.